Hello, science fans. Let's do some more reverse engineering of the universe. Today's study, titled Vacuum Composition, questions assertions that perfect vacuum and almost all of the volume of a single atom are empty space, quote unquote. This study is a replication of a previous simulation experiment titled Matter Creation Sequel. Perfect vacuum was defined as total energy density minus electron and nucleon particle density after cooling to 0 Kelvin. How is this done? The binary mechanics lab simulator was used to simulate a 72x spot volume with vacuum mode. In vacuum mode, energy radiating from the simulated volume was lost, as if this volume was located in absolute vacuum and quanta could exit but not re-enter the simulated volume. Thus, initial quanta density, where quanta are one-state bits, in the simulated volume gradually decreased to a final density. We call these quanta exiting the volume out bits, and they may represent particles in motion or electromagnetic radiation leaving the simulated volume. When the process completes, the system state, called the bit function, in the simulated volume is deemed to have cooled to 0 degrees Kelvin. Vacuum density was defined as the final density after cooling to 0 minus the particle density. And the paper gives the formula for the particle density and details about that. Figure 1 of the results shows the energy density range in the initial setup. Absolute vacuum is, of course, at 0, which means there are 0 energy quanta in the simulated volume, and that would qualify, yes, as empty space. We can go all the way up to initial density at 1, which means that every single bit locus has an energy quanta in it. So here's our energy density range. We can parse this starting with the observed proton mass, which was reported in the paper on proton-electron mass ratio, up to the plasma range and the lepton higher energy lepton quark soup range. Notice that in this mid-range here, the final density after cooling to 0 Kelvin is rather constant, sort of a plateau here. And when we go up to higher energies, this steps down to a lower level in the final density. And the most energetic energy densities, even further, it steps down to lower levels after cooling to 0 Kelvin. Here we show the percent kinetic energy before cooling, the percent vacuum after cooling to 0 Kelvin. In this lower energy density range, you can see that 10% or less of the energy quanta are lost during cooling. And as we move up from the observed proton mass point, the amount of energy increases all the way up to about 95% in the initial state, which is deemed to be kinetic energy because those quanta are lost after cooling. Now, the punchline here is we have a relatively constant, about 88% of the total energy after cooling is perfect vacuum. It's not empty space. Here we show the proton counts versus an initial density, and you can see that they rise rapidly, reach a certain plateau, and then in the plasma range, there's a reduced final proton count after cooling, and even more so in the most high energy density ranges. We see that the threshold quanta density for baryogenesis, the formation of protons and nucleons, is about 0.7 initial density. So I'll go so far as to say goodbye to the empty space model. This report debunks the myth that perfect vacuum and almost all of the volume of a single atom are empty space. Instead, the data suggest that empty space is literally teeming with energy quanta, even at 0 Kelvin temperature. Specifically, about 88% or more of final state quanta is perfect vacuum energy content. This energy content after cooling amounts to about 21% of maximum possible density at initial densities above the observed proton mass level at 0.25 and below the plasma level at 0.6. Hence, the empty space model of perfect vacuum can claim that some 79%, in other words, 100% minus 21%, of the bit loci are in the zero state, which we would call neutrino bits, and might be described as, quote, empty. Nonetheless, the present data appear to be inconsistent with the empty space model of perfect vacuum, and to lend support for the notion that perfect vacuum at temperatures above 0 Kelvin may act as a sea of virtual particles. In the present context, the empty space model of perfect vacuum might seem rather naive. This report illustrates how space-time energy quantization in binary mechanics, which we call full quantum mechanics, may provide unprecedented methods for quantitative study of partial and perfect vacuum components of a system state. Now, when things explode, when the BMLS is run in vacuum mode, initial state energy density content is not contained. At the substantial higher initial densities in the plasma and lepton quark soup ranges, which, by the way, they call quark gluon soup elsewhere, the cooling process begins with impressive explosion or blast events where quanta are forcefully extruded from the simulated volume. As a result, when cooling reaches 0 Kelvin, both nucleon particle density and overall particle and perfect vacuum densities were found to be much less than observed in the lower 0.25 to zero point 0.6 initial density range. Further, in the highest energy lepton quark range, there was greater reduction in both particle and vacuum final densities compared to the plasma initial density range. The reduced final state particle and vacuum densities from plasma and lepton quark soup initial states may pertain to expanding universe questions. For example, massive explosions such as supernova may result in vast volumes with reduced particle and vacuum densities compared to, say, other regions of outer space, much less near STP, that's standard temperature pressure, laboratory environments. First, light speed appears to be affected by quanta density, another victory of space-time energy quantization. See the LIGO paper on that. Second, the high quanta content of perfect vacuum, approximately 21% of maximum energy density found in this report, may pertain to dark matter speculations. Third, huge volumes with reduced quanta density in outer space could have significant implications regarding assessment of gravitational effects pertinent to expanding universe questions and galaxy formation and shape. Finally, recall that volumes with lower vacuum energy densities would eventually normalize by absorption of incoming quanta captured by electron and proton bit cycles. And there's a paper on that if you haven't looked at that. Now, I ask in conclusion, is reverse engineering the universe fun or what? Thanks for watching.